Now, in this lecture, we'll answer on two questions. In the first question, we find out the area of this semicircle that is inside quarter circle AOB. And in the second question, we find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing, we have a quarter circle AOB. We know that side AO equals to 5 units in its length. That is to say, the radius of this quarter circle is equal to 5 units. And inside this quarter circle AOB, we have this semicircle. And our mission is to find out the area of this semicircle. So, first of all, we will define the center of this semicircle. This point is point C. We will define the touching point of this quarter circle with this semicircle. This point is point F. We will define the touching point of this semicircle with the quarter circle. This point is point G. Likewise, we will find the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we will define the point of tendency of tangent BO with this semicircle. This point is point L. In the next step, we will define the radius of this semicircle as X. Therefore, CF equals to CG. They are both the radii of this semicircle. Therefore, each of those two maximums is equals to X. So, CF equals to X. CG also equals to X. In the next step, we'll join point C and L together by a straight line. CL is of course the radius of this semicircle, is equals to X according to our definition. Likewise, we'll join points C and H together by a straight line. CH is also the radius of this semicircle, is equals to X. So here we have the radius CH that is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HG. If AO is perpendicular to HG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing these constructions, we created here quadrilateral C edge OL. Inside quadrilateral C edge OL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral C edge OL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral C edge OL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle C edge OL, side C edge equals to side OL. But C edge equals to x, therefore OL must be also equal to x. Likewise, according to the same rule, in the same rectangle C edge OL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So we actually found out that quadrilateral CHOL is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. In the next step, we join points O and C together by a straight line. By joining points O and C, we created here the right and associated triangle, triangle CLO. So I'll copy this right and associated triangle, triangle CLO in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle CLO. Here by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Actually, this is the right and associated triangle, triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. So I'll write it down. CO squared equals to CL squared plus LO squared. CO is the missing side, so we leave it as it is. CO squared equals to CL squared. CL equals to x, therefore CL squared is x squared plus LO squared. LO is also equals to x, therefore LO squared is x squared In total, CO squared equals to x squared plus x squared, that is 2x squared. So actually found out that CO squared equals to 2x squared. Here we take a root out of this equation and finally get that CO equals to the square root of 2 times x units in its length. So this is line 7 CO. The length of line 7 CO is square root of 2 times x. We know that point O is the center of the quarter circle. So from the center of the quarter circle, that is to say from this point O, we have line segment OC that bisect chord FG. That is to say, line segment OC divides chord FG into two halves. Each half equals to x. And therefore we can implement here rule 7. So I think quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisect a chord, then the line segment is also perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of this circle. From the center of the circle, that is to say from this point O, we have line segment OM that bisect chord AB. That is to say MA equals to MB. And therefore, according to this rule 7, line segment OM is also perpendicular to AB. If OM is perpendicular to AB, it means this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 7. So whenever you have a line segment that is drawn from the center of the circle and it bisects a chord, then that line segment will be also perpendicular to that chord. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have line segment OC that is drawn from the center of this quarter circle, that is to say from this point O, and line segment OC bisect chord FG. And therefore, according to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, we will join points O and F together by a straight line. So, what is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, and know that the radius of the quarter circle is 5. So therefore, OF equals to 5. In the next step, I'll copy the right and green triangle CFO in a new page, and we'll implement the Pythagoras theorem on this green right triangle CFO. side CF equals to x. Found out that side CO equals to the square root of 2 times x. And the hypotenuse FO equals to 5. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right and green triangle CFO that I copied from the original drawing. In this right triangle CFO, according to the Pythagoras theorem, f all squared, that is the square of the hypotenuse, equals to fc squared plus c all squared. Again, f all squared equals to fc squared plus c all squared. So I'll write it down. F all squared equals to cf squared plus c all squared. The hypotenuse FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to CF squared. CF is x, therefore CF squared is x squared plus CO squared. CO is square root of 2 times x, therefore CO squared is square root of 2 times x squared, that is actually 2x squared. So in total we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So 3x squared equals to 25. Here we divide this equation by 3. And finally we get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle that is inside quarter circle A or B. So what is the area of the semicircle? The area of the semicircle must be equal to pi x squared over 2. So I'll write it down. The area of the semicircle, that is the area that we are looking for in this question. It is equal to pi x squared over 2. So it is pi over 2, and we just right now found out that x squared equals to 25 over 3. Therefore, we will substitute x squared in this equation by 25 over 3. Okay, we found out that in total, the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So it is 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. Again, if we found out that the area of this semicircle is equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. We finished with the first question. In the next step, I will present to you the second question and we will solve it. Our mission in the second question is to find out the area of this green shape. So, in the drawing, we have rectangle ABCD. We note that side AB of this rectangle ABCD equals to 5 units in its length. In addition, we know that inside this rectangle ABCD we have this semicircle and this quarter circle. Again, our mission is to find out the area of this green shape. So first of all, we will define the radius of this quarter circle PBC as x. the radius of quarter BC equals to x, that is to say BC, that is the radius of the quarter circle, equals to x. BC equals to x according to our definition. We know that all the angles inside any rectangle are right angles. So this angle is a right angle. It is one out of 4 angles inside rectangle ABCD, therefore it is a right angle. Likewise, we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. So already known, DC equals to 5 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD equals to x. AD is one side of rectangle ABCD, but AD is also the diameter of the semicircle. So we know that the diameter of this semicircle equals to x. If the diameter of this semicircle is x, then the radius must be equal to half of it. So the radius of this semicircle must be equal to x over 2. We will define the center of this semicircle. This point is point O. We know that the radius of this semicircle is equal to x over 2. So the radius OA equals to x over 2 units in its length. And the radius OD also equals to x over 2 units in its length. So in the drawing, we have actually an external match between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. We define this point, that is their touching point, as point S. So in the drawing, we have an external match between the semicircle and the quarter circle. And whenever you have an external match between two circles or semicircles or quarter circles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing, we have two circles, and they have an external match between them at point P. That is to say, they touch each other externally at point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects their centers together is, of course, the straight line OM. And this straight line OM, according to this rule 10, must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM, according to this rule, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, again, we have an external match between the semicircle and the quarter circle. For that reason, we can implement a rule 10. The center of this semicircle is at point O, the center of this quarter circle is here at point C, and the straight line that connects the centers together is, of course, the straight line CO. And according to rule 10, the straight line CO must pass through point S, that is their touching point. Again, according to rule 10, the straight line CO must pass through point S, that is their touching point. So we join points O and C together by straight line, and we know that according to rule 10, the straight line OC must pass through point S. It's very easy to see from the drawing that indeed the straight line OC passes through point S, that is their touching point. The touching point of the semicircle with the quarter circle. So if OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC must be equal to OS plus SC. So I will write it down. OC, according to rule 10, it must be equal to OS plus SC. So OC equals to OS. OS is of course the radius of this semicircle, that is equal to x over 2. So here OC equals to OS, that is x over 2, plus SC. SC is the radius of this quarter circle, and according to our definition, the radius of this quarter circle equals to x. So SC equals to x. So here OC equals to S to OS plus SC. So OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is 1.5x, or 3 over 2x. So in conclusion, we found out that OC equals to 3 over 2 times x units in its length. So this is line segment OC, that equals to 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC in a new page, and we'll implement the Pythagorean theorem on this right triangle ODC. Side OD equals to x over 2 units in its length, side DC equals to 5, and the hypotenuse, we just write down found out that the length of the hypotenuse DC is 3 over 2 times x units. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle ODC that I copied from the original drawing. This right triangle ODC, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. Again, OC squared equals to OD squared plus DC squared. So I write it down. OC squared, the square of the hypotenuse, equals to OD squared plus DC squared. OC is 3 over 2 times x, therefore OC squared is 3 over 2 times x squared, that is actually 9 quarters times x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, if we found out that 9 quarters times x squared equals to 1 quarter times x squared plus 25. Here we will subtract x squared over 4 from this equation, and we get that 9 quarters times x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, and 2x squared equals to 25. Here we divide this equation by 2, And finally we get that x squared equals to 25 over 2. X squared equals to 25 over 2. Here we take a root out of this equation and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in total we found out that x equals to 5 over square root of 2 units in itself, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So, what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I write it down. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the green shape equals to the area of rectangle ABCD. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is AB, that is 5. The width is BC, that is x. So in total, the length times the width is 5x. So the area of rectangle ABCD equals to 5x minus the area of this semicircle. The radius of this semicircle is x over 2, therefore the area of this semicircle must be equal to pi times x over 2 squared divided by 2. So I write it down. The area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2. Minus the area of this quarter circle. What is the area of the quarter circle? We know that the radius of this quarter circle equals to x. And therefore the area of this quarter circle must be equal to pi x squared over 4. So I write it down. The area of the quarter circle equals to pi x squared over 4. So in total, the value of this expression that is inside the brackets is the area of the green shape. So what is the value of this expression? Here we have 5x minus pi x over 2 squared is x squared over 4. So in total, this expression will be equal to minus pi x squared over 4 multiplied by 2 minus pi x squared over 4. So the area of the green shape in total will be equal to 5x minus here, this expression in total equals to minus x squared over 8, because 2 times 4 is 8, so it is minus pi x squared over 8 minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2. And we get that this expression will be equal to minus 2 pi x squared over 8. So in total, the area of the green shape equals to 5x, and we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, we found out that the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2, and x equals to 5 over square root of 2 units in its length. Therefore, we can substitute x in this equation by 5 over square root of 2, and x squared in this expression by 25 over 2. We'll do it now, and we get that the area of the green shape in total will be equal to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we should find out that the area of the green shape equals to, here we have 5 times 5 is 25, so in total this expression equals to 25 over square root of 2, and here we have, in the numerator of this expression, we have minus 3 pi times 25 is minus 75 pi, divided by 2 times 8, that is 16. Okay, so in total we found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. The value of this expression in terms of numbers, this expression equals to 2.95 square units. So in total we found out that the area of this green shape equals to 2.95 square units. We finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this semicircle that is located inside this quarter circle A or B. So in the drawing we have a quarter circle A or B. We know that the radius of this quarter circle equals to 5. And inside this quarter circle we have this semicircle, and our mission is to find out the area of this semicircle. So first of all we define the center of this semicircle. This point is point C. We define the touching point between this quarter circle and this semicircle. This point is point F. We define the other touching point of this semicircle with this quarter circle. This point is point H. We define the point of tendency of tangent BO with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we define the radius of this semicircle as x. Therefore, CF equals to CG equals to x. The above the area of this semicircle that is equals to x according to our definition. In the next step, we join points C and N together by straight line. CL is of course the radius of this semicircle that is equals to x. Likewise, we join points C and H together by straight line. CH is also the radius of this semicircle that is equals to x. So here we have the radius CH that is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CL of this semicircle that is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we can take quadrangle CH OL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth cylinder, in total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth cylinder must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, not a square. So we relate to quadrilateral CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the same rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So we actually found out that quadrilateral CHOL is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side equals to x. In the next step, we join points O and C together by side line. By doing this construction, we actually get there the right and associated triangle, triangle CLO. In the next step, I copied this right and associated triangle, triangle CLO in a new page, and we implemented the Pythagoras theorem in this right and associated triangle, triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So actually, this is the right and associated triangle, triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO square, that is the square of the hypotenuse, must be equal to CL square plus LO square. Again, CO square equals to CL square plus LO square. CO is the missing side, so we leave it as it is. And it is equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total, CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. Here we took a root out of this equation and finally found out the missing hypotenuse CF, the length of the missing hypotenuse CO is equals to the square root of 2 times x units in its length. So this is CO, I said CO equals to the square root of 2 times x units in its length. So here we know that point O is the center of the quarter circle. So from this point O that is the center of the quarter circle, we have here line segment OC that bisects chord GF. That is to say, line segment OC divides chord GF into 2 halves. Each half equals to x. And therefore we can implement a rule 7. So I'm clicking on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment may be also perpendicular to that chord. So in the drawing here a circle, this is point O, that is the center of this circle. From the center of the circle, that is to say from this point O, we have line segment OM that bisects chord AB. That is to say, MA equals to MB. And for that reason, because of the fact that line segment OM that is drawn from the center of the circle bisects chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle, and it bisects the chord, then that line segment will be also perpendicular to that chord. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, we have line segment OC that is drawn from point O, that is the center of the quarter circle. So line segment OC bisects chord FG. That is to say, it divides it into 2 halves. Each half equals to x. And therefore, according to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 7. we know that the radius of the quarter circle equals to 5 because AO, that is the radius of the quarter circle, equals to 5. We join points O and F together by straight line. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends in point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, that equals to 5. In the next step, I copied the right and green triangle CFO in a new page and implemented the Pythagoras theorem on this right green triangle CFO. So actually, this is the right and green triangle CFO that I copied from the original drawing. The hypotenuse FO is 5, CF equals to x, and CO equals to the square root of 2 times x. According to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, equals to CF squared plus CO squared. Again, FO squared equals to CF squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to CF squared. CF is x, therefore CF squared is x squared, plus CO squared. CO is equal to 2 times x, therefore CO squared is equal to 2 times x squared, that is 2x squared. So in total, 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So in total, we found out that 3x squared equals to 25. Here we divided this equation by 3, and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. We know that the radius of this semicircle is x, and therefore the area of the semicircle must be equal to pi x squared over 2. So the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared, and x squared is 25 over 3, therefore substitute x squared in this equation by 25 over 3, and we actually found out that in total the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So in total the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of the semicircle, the area of this semicircle that is located inside quarter circle AOB is equals to 13.09 square units. So we finished with the first question. In the next step, I actually presented to you the second question, and we solved it. In the second question, our mission is to find out the area of this main shape. So, in the drawing, we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. The semicircle touches the quarter circle at this point S. Again, our mission is to find out the area of this green shape. So first of all, we define the radius of this quarter circle as x. Therefore, BC, that is the radius of the quarter circle, equals to x according to our definition. We also know that ABCD is a rectangle, and all the angles inside any rectangle are right angles. So this angle is a right angle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. Likewise, according to the sum rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x. If the diameter is x, it means that the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to x over 2. We define the center of this semicircle, this point is point O. So the radius OA equals to x over 2, and the radius OD also equals to x over 2. Here, in the drawing, we have an external arch between this semicircle and this quarter circle. That is to say, they touch each other externally in this point S. And whenever you have an external arch between two circles or semicircles or quarter circles, you can implement rule 10. So I'll put quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles and they touch each other externally at this point P. The radius of this circle is 0.0. The radius of this circle is 0.m. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM that connects the centers together must pass through their touching point, that is point P. Or OPM is one straight line. Again, according to rule 10, OPM is one straight line. So we can actually implement rule 10 in our drawing. Because in our drawing you have an external arch between the semicircle and this quarter circle. That is to say, they touch each other externally at this point S. Therefore, we can implement rule 10. The center of this semicircle is 0.0. The center of this quarter circle is 0.C. And the straight line that connects the centers together is of course the straight line OC. And this straight line OC must pass through point S, that is their touching point. Again, the straight line OC must pass through their touching point, that is point S. Or OSC is one straight line. Again, according to rule 10, OSC is one straight line. If OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC according to rule 10. So OC equals to OS. OS is the radius of this semicircle, that is x over 2, plus SC. SC is the radius of this quarter circle, that is x. So in total, we actually found out that OC equals to x over 2 plus x, that is 1.5x or 3 over 2x. So OC equals to 3 over 2 times x units in its length. In the next step, I copied the right triangle ODC in a new page and implemented the Pythagoras theorem in this right triangle ODC. So this is the right triangle ODC that I copied from the original drawing. Again, the hypotenuse OC is 3 over 2x units in its length. Side OD equals to x over 2 units, and side DC equals to 5 units in its length. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. Again, OC square equals to OD square plus DC square. OC is 3 over 2 times x, therefore OC square is 3 over 2 times x squared, that is 9 quarters times x squared. And it is equals to OD square. OD is x over 2, therefore OD square is x square over 4 plus DC square. DC is 5, therefore DC square is 5 square, that is 25. So in total, we found out that 9 quarters x square equals to 1 quarter x square plus 25. Here we subtracted x square over 4 from this equation, and finally found out that 9 quarters x square minus 1 quarter x square equals to 8 quarters x square, and it is equals to 25. Because x square over 4 minus x square over 4 is 0. So 8 quarters x square equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared. This equals to 25. 2x squared equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. Here we took a root out of the equation and finally found out that x equals to the square root of 25, that is 5 over square root of 2. So in total we actually found out that x equals to 5 over 2 units in itself, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. What is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Again, the area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Here, the area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length is AB, that is 5. The width is BC, that is x. So in total, the length times the width is 5x. So the area of rectangle ABCD is 5x. Minus the area of the semicircle. What is the area of the semicircle? You know, the radius of this semicircle equals to x over 2, and therefore the area must be equal to pi times the radius squared over 2. So it is pi times x over 2 squared divided by 2. So in total the area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2. Minus the area of the quarter circle. We know that the radius of this quarter circle is x. And therefore the area of this quarter circle must be equal to pi x squared over 4. And again the area of the quarter circle equals to pi x squared over 4. So in total, the expression that is inside, that is between those two brackets, is the value, is the area of the green shape. So what is the value of the expression that is between those two brackets? We have here 5x, and we have here minus pi times x over 2 squared. X over 2 squared is x squared over 4. So in total, this expression equals to pi x squared over 4 times 2. Pi x squared over 4 times 2. Minus pi x squared over 4. So it is 5x. Here this expression equals to pi x squared over 8, because 2 times 4 is 8. So it is minus pi x squared over 8. Here we multiplied both the numerator and the denominator of this expression by 2. So after we multiply it by 2, we get that this expression equals to 2 pi x squared over 8. So in total the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. And therefore we can substitute x in this equation by 5 over square root of 2 and x squared in this expression by 25 over 2. We did it, and we found out that 5x is 5 times 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total, the area of the green shape equals to the value of this expression. This expression is equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. And here we have, in the numerator of this expression, we have 3 pi times 25, that is 75 pi, and in the denominator we have 8 times 2, that is 16. So in total we shall find out that the area of the green shape equals to 25 over square root of 2 minus 35 pi over 16 square units. Or in terms of numbers, the value of this expression is 2.95. And therefore we shall find out that the area of this green shape equals to 2.95 square units. Okay, thank you very much.